have a case study example on how the cell has to be selected, how it has to be derived from the specification of the battery pack. So without you have a specification of a battery pack, you cannot choose a cell. So it's important to understand the specification of the battery pack very much. So now we'll understand what is the case study for cell selection. So over here we have a requirement of battery pack which is 630 to 640 volts, 200 Ah. And we also have C rate, which is charge and discharge rate current requirements, which have been split into two, which is continuous and peak charge rates. So when we say continuous charge rates, it's basically for a very small amount of time, which is like constant speed, which is a standard current during charging or discharging, which happens for a very long time. Whereas peak rate is specifically for a very small amount of time, like 1C or 3C or 2C, which is done for a period of 20 seconds, 30 seconds or 40 seconds or maybe 1 minute, not more than that. So that is one of the reason why the cell delivers high currents for a short period of time, but when that happens for a longer period of time, the cell deteriorates quickly. So that is what cell selection is based on. Like, it is important for you to, for everyone who is working on this, to understand what are the continuous C rate requirements and what is the peak C rate requirement, like 1C, 2C, 3C for 30 seconds or however it is. So this is something which has to be evaluated. And then we have battery pack space available, 1.7 meters and 1.75 meters and 0.3 meters height. So let us get back into C rate requirements for some more time and understand what is it. So when we say continuous C rate, 0.5 C charging and 1 C charging, which means when you are charging the battery pack at 0.5 C is like 0.5 C times of 200 Ah. Like, you have a battery pack of 200 Ah capacity and you are charging it 0.5 times of it, which is 100 amperes. So when you are charging the battery pack of 200 Ah with 100 amperes, the time taken would be 2 hours. Whereas if you are charging the battery pack of 200 Ah at 1C, which is 1 times 200, which means you are going to discharge it at 200 amperes and it's going to take 1 hour for that. So it's all matter of 0.5 C or 1 C. If you're going to charge it at 0.5 C, it's going to take 2 hours, and if you're going to discharge at 200 amperes, it's going to be discharged in 1 hour. Similarly, the same is the case with peak charging. When you're going to charge it at 1C, that is for a very limited time, say 30 seconds. That means you're going to charge it for 200 amperes within just 30 seconds of time. When you're discharging at 1C, charging at 1C is not a problem. But when you're discharging at 3C, that is for 30 seconds, that is where you need to understand how this is going to function, how the cell is going to work. So that is something which you'll have to understand from the cell point of view. And then yes, we have the space availability, which is length is 1.7 meters, 1.75 meters width and 0.3 meters height. And then the whole pack has to be something around 900 kgs. So that is the weight requirement of this whole battery pack. Now another important part is like operating temperature. The battery pack must be operating only between minus 20 degrees to 55 degrees. Since the cell while charging and discharging generates a lot of heat because of the ions, electrons movement, and the electrochemical reactions keep on happening, it is very important for the cells and the modules to keep with the optimum temperature. And that's how you need to also decide on the cooling technique which is needed for keeping the cells within the optimum temperature. So that's how your cooling technique is also decided, which is basically active cooling for the high voltage, because these are high voltage packs and high capacity packs which are operating at 200 amperes of discharge and 600 amperes for 30 seconds, which is too high. So you need to have an active cooling for this, which means active cooling is like you have a cooling plate where water flows throughout it continuously so that the heat generated by the cells is always taken out. And then you have the location where it is going to be mounted. So here it could be either on the rooftop or chassis, and the life cycles that is to be achieved is 300 life cycles. So that means 300 cycles of charge and discharge at a continuous C rate condition, which is 0.5 C and 1 C discharge. So how do we select the cell? So here is a cell specifications which we have selected. So there could be a lot of cells. So that is something which we have a lot of database, and you could also find out different cells which are available. So when we select the cell, we have selected a prismatic cell, which is LFP cell. And how do we know that? It's from the voltage over here, which is a typical voltage of 3.2 volts. So we have a cell which is 3.2 volts and it has a capacity of 105 volts. So we have chosen the cell, and when we choose the cell, we can also determine what is its voltage, what is its maximum voltage, what is its minimum voltage. So basically this is a cell specification sheet which we have figured it out, and from this cell specifications we need to match what the battery pack specifications are. Now if we see a typical voltage of this, which is 3.2 volts, we can see that if we put 200 cells in series, it would match what our battery pack requirement is, which is 630 to 640 volts. We could go there now. If we see, the requirement is 630 to 640 volts and 200 Ah. So that is a requirement. So for us, if we have 200 cells in series and 2 cells in parallel, we are going to match the requirement. So the voltage and capacity requirement are met. Then we go to the continuous current, which is charge and discharge. So the requirement for a continuous charge current is 0.5 C and discharge continuous is 1 C rate. So here we have met that continuous C rate conditions also. Now we'll see what a peak charge current is, which is 1 C rate, and peak discharge is 3 C rate. But we have a conditions over here which says it's based on temperature and SoC. So what does that mean? We'll go and refer what is that based on temperature and SoC in the next slides. And then once we have this condition met, the other important part is going to be the operating temperature. So we have to maintain the whole cell and the battery pack within the operating temperature of -20 to 55 degrees centigrade. So even the battery pack requirements calls for the same. The cell requirement also is the same. Typically, mostly the lithium-ion cells are always operating between -20 to 55 only. So that is something you'll find it common everywhere. And the life cycles at 100% SoC is something which you can get 3500 cycles. So usually the requirement which we saw was like 3000 cycles. But here we can get 3500 cycles at continuous series conditions, which is kind of, we have met that as well. So when we see like the whole cell voltage window, it is from 2.5 volts to 3.65 volts. We can understand that the usable capacity is 106.5. But over here, see that the recommended SoC window is from 10% to 90%, which means if you do not use the cell from 2.5 to 3.65, that means you will not use the first 10% and you will neglect the last 10%. Then you'll have a little bit reduction in the capacity. So which means when you are always operating from the whole voltage window, from bare minimum to the whole maximum, you will always have stresses. So that is common everywhere. If you are going to use it to the full capacity, the system which you would be using, any system, be it your mobile or a bike, anything, if you are always going to operate at higher thresholds of it, you are going to deteriorate the system much faster. The lives of the whole system gets affected. So that is something which you will have to consider. Like over here they have said that recommended SoC window is 10% to 90%. So that is something which you can consider or not, or you need not follow the same. You can make your own. Instead of 10% to 90%, you can start from 5% to 95%, which means you are still reducing the stresses which we would have. Like you have reduced the 5% stress at the lowest level and you have reduced the 5% stress at the top level. But literally this is something which is used everywhere to limit the operating voltage window. So basically the ends of the voltage are never touched. The cell should never see the ends of the voltage. If you allow that, you are still going to get the typical capacity, but the life cycles could go for a toss because you would deteriorate the cells much faster. So the selected cell over here seems to be much appropriate when we consider the major parameters like C rates, where life cycles play a very vital role. So it is something which you have to consider. And also the dimensions of the cell, which is like 130 or 36.7 and 200.5 mm height. So assuming that this is the right fit, this could also fit into the whole battery pack with these dimensions. You will have to do a rough calculation over here and see whether you can fit 400 cells, like 200 cells and 2 cells, which gives 200 into 2, which is 400 cells. See whether you can put 400 cells in that pack or not. That is something you can do a rough calculation and you can figure it out. Yes, it can still work out. So that's how you arrive at this cell. Now, we talked about dependent on temperature and SOC percent. When we talk about peak charge rates, we talked about that. Now, what does that mean? What does that peak charge rate mean when we say it is temperature and SOC dependent? That is what we saw in the previous slides, that the cells are based on temperature and SOC, which means that a cell certainly has a capacity of delivering or absorbing the current at high C rates, but it is dependent on SOC percent, which is nothing but the state of charge and the temperature of the cell that is needed at the time of delivery. Over here, which we have SOC percent on the x-axis. Over here we have 100, 90, 80 and so on going up to 0, and then we have temperature on y-axis, which is from 55 degrees reducing to 0 degrees. But over here you might have observed one interesting thing, that is, for charging, you can see the temperature is from 0 degrees to 55 degrees. So this is how the charging works. So during charging, lithium-ion cells are not great when it is below 0 degrees. So at below 0 degrees, you do not recommend the cell to charge. You either use heater plates, you heat it above 0 degrees and then you start the charging. That is what the lithium-ion cell chemistry has a disadvantage in charging, because most of the lithium-ion cells have electrolyte filled, and those electrolytes, when these are freezed, the ion movements become quite difficult. So that is how you say, like, below 0 degrees lithium-ion cells should not be charged. So that is how it is. Now when we get back to this peak charge rate characteristics, which is dependent on SOC percent and temperature, over here we have seen, like, in x-axis we have SOC, y-axis we have temperature, and if you refer the first one, like the 55 degrees line, when it is at 100% SOC and 90% SOC, what is charge? Like, if you have a vehicle, you have connected the charger and you're trying to charge it. That's what the charging is. So when you have at 100% and 55% you have connected the charger, literally do not take any charge because you're already at 100%. But when you're at 90%, it takes only 10.5, and that goes on continuing up to 60 degrees. So till 60% SOC at 55 degrees, your cell would only accept 10.5 amps of current, which is just 0.1 C. And when it is from 50% to 0% SOC, your cell will accept only 21 amps of current, which is 0.2 C. So you have a capacity of 105 Ah, but the cell is having 0 SOC. There is no charge in there, but it will still take 21 amps of current only, which is 0.2 C. Why is it? It is mainly because of the temperature. Because your cell is at very high temperature, 55 degrees, if you charge it even more, the temperature is going to hike even more. So this is certain condition which you will have to program in the BMS as a safety precaution, saying that if your cell is at 55 degrees, you will not be charging it more than 0.1 C or 0.2 C. If you do that, you are going to raise the temperature of the cell, which is going to lead to some disastrous effects after that. And then after, if you see 50%, so these are all the cell characteristics. This is all coming from a cell testing window. So a cell has to be extensively tested, and this are something which has to be found out. What are the limitations of the cell? So now see, if we want to charge it, the requirement was just 1 C. And if you see at 25 degrees, when the SOC is at 70%, you can charge the cell at 3 C. This is huge, this is great. But it also has to be at a 25 degree temperature. And if you see at 45 degrees, you can charge the cell when it is from 50% to 0% SOC, you can charge it at 105. But the moment you cross 50%, you should not allow the cell to be charged at 1 C rate. You should allow the cell to charge at 0.5 C rate. That is the limitation of this chemistry, or the limitation of the cell. That means the cell is capable of doing that up to a certain limit, or a voltage or a SOC percent or a temperature window. So that is something which you have to program it in the BMS, saying these limitations, like at 25 degrees, and if the SOC is lower than 80%, then only I will be charging at 3 C rate. Or else if it is increasing, the moment it crosses 70 degrees, I'll charge at 1 C. The moment it crosses 80% SOC, I'll charge it at 0.5 C. This is something which you have to pick these tables. This could be a lookup table for you, and you can program your BMS accordingly, which would make the whole battery pack function accordingly. So that means if you have a charger and the state of that battery pack is at 55 degrees and you have only 30% SoC and you want to quickly charge the cell or the battery pack, you can charge it at only 0.2 C, which means you'll have to bring down the temperature to certain 45 degrees or 25 degrees to charge it even more quickly. So that is the action which you have to take, and that is dependent on the BMS, how you program it. The more and the more better you program the BMS, the more testing data you have, the better would be the result coming, the better would be the operation of the battery pack. Now this is for the peak charge rate. Now the similar is something which is for the peak discharge rate. So over here, if you see, it's interesting that the temperature has now gone from minus 20 degrees to 55 degrees, whereas charging was from 0 to 55, but the discharge is from minus 20 to 55. So up to minus 20 degrees or sub-0 degrees, the discharging can happen. That is the gist of lithium-ion cell chemistry. So lithium-ion cells can actually discharge cells at minus 10, minus 20 degrees. But one important point over here is, if you see at minus 20, your C rates have fallen way below. So it is till minus 10 C also it can deliver 1 C. But if you see at higher C rates, like at 100% SoC, so it is opposite of discharge. When you are charging the cell, if it is 0%, you should see the first 50% has all higher values and the next 50% has lower values, because your cell has already been charged up to a certain amount, and when it is filling up, which means, for example, you have a glass and you are filling it with a filter water, you are filling it. So what do you do usually? You keep the tap open until it is getting filled 50%, 60%, 70%, and the moment your glass is almost about to fill, you will put your hand on the tap to close it slowly. So you will allow the water to slowly fill and then you close it. So this is doing the same. This is your charger which is doing the same functionality. So when the battery is fully empty, you are charging it fully, and when it is slowly nearing to its 100%, you are going to give the charge slowly so that you will reach the 100%. So it is the same. But whereas when it's a discharge, what happens is you are already at a very full level, you have full amount of charge, and when there's a tank which is fully loaded with water, and when you open the tank, what happens is there's a huge rush of water coming out. It's the same. When you have a full charge cell, no matter you're at 25 degrees, 55 degrees or 10 degrees, the energy or the power which that can be drawn from a cell is huge. So that can be reflected over. You can see for a 55 degrees, when the cell is at 100%, 90%, 80% SoC, you can get 5 times, 5C of the current is coming up. But remember, this peak C rates and peak discharge rates are for limited time, that is 30 seconds only. So you'll get 5C for 30 seconds, and then from 70 to 60% SoC, you'll get 4C. And then from 50% to 10%, it's slowly reducing, 3C, 2C and 1C. Similarly, at 25 degrees, you observe the same. Now, there is a change over here, 25 degrees to 55 degrees. If you see, the 5C delivery can be up to 60% for 25 degrees, because your cell is at a very good optimum temperature. Whereas at 55 degrees, that is the top point of the optimum temperature, there is some limitation applied over there. So over here, there is another thing. If you are reaching to the nearest lowest SoC, you should not be drawing more power, because you will be abusing the cell. That's the reason your C rate reduces as the SoC reduces. But the same is opposite in charging. If you're nearing to the 100% SoC, you should not be charging at higher C rate. You should reduce your C rate so that you don't abuse your cell. So this is something which you have to take care. So there's a C rate. When you are nearing to 100%, you charge it slowly. When you are discharging and you are nearing to 10%, 0%, you discharge with a lower current. So that is how you program your BMS accordingly, so that you don't abuse the cell much. You are operating the cell in a very good optimum operating zone, so that there is no abusing of the cell, which can give you the life cycles as expected. So till now we have selected the cell depending on peak C rates, etc. Now we'll understand what is the cell selection based on life cycles and SoC. So when we see the first graph, we have life cycles 0 to 4000, and we have capacity retention window, which is 0, 60% to 105%. So here, as per the data sheet which the cell says, which says that by the end of 3500 cycles, you'll have a capacity retention of only 82%, which means if you use it further, your capacity will fade out and you will be losing a lot of capacity. You will not be able to use the complete capacity. So usually in EV also, you stop using the cell when it reaches 80% of capacity retention, and then later on you can use it for any of the storage applications. But one important thing that you wanted to consider over here is, when you have 3500 cycles at a capacity retention of 80%, which is when you have used the cell for a complete voltage window, 2.5 volts to 3.6 volts at a standard operating condition of C rates, which is 0.5 C and 1 C discharge. So at that rate, if you are using the whole voltage window, 2.5 volts to 3.6 volts, this would give you 3500 cycles. But if you also remember, there is a certain recommendable window which is 10% to 90%. That is what a recommended window was given by the cell manufacturer. So if you do that, what you would do is this stress, the box, which is the red box, is something has been highlighted so that you limit the cell voltages. But what would happen is every capacity available about 3.4 to 3.6 volts is taken away. You will not be able to use that. And all the capacity which is from 2.55 to 2.5 volts is all gone. You cannot be using that also. So which means you are going to limit yourself to the 2.55 volts to 3.4 volts, and essentially the capacity lost is lost. So that is something which you will have to understand while doing that. So if you have a cell which is like 106.5 capacity, AH capacity over here, and by limiting the cell voltages to 2.55 to 3.4, there is some percent of capacity being lost. But your need is 200 AH. You have selected a cell of 106.5 AH, which is typical, and minimum capacity is 105 AH. So when you reduce this kind of voltages like this, you lose some percent, like 5% or 10% of the capacity. Which means if you have two cells put in parallel, which is 105 AH into 2 becomes 210 AH, you are already 10 AH higher than what you need. So by limiting these voltages, you will lose some capacity, but still you will have your required 200 AH capacity there. By doing such kind of selection of a cell which is slightly higher than what is required, what you can do is you can always limit your voltages to a recommendable SoC like 10% to 90%, so that even though you lose your capacity, you are still meeting your required capacity. And one major advantage of that is your life cycles are going to still increase, because this life cycle of 3500 is from 2.5 to 3.6. But definitely if you're not going and meeting the ends of the life cycle of the voltages, your life cycles are definitely going to increase much more. So this is an advantage which you could do. This is something which is in your hands. You can program the BMS accordingly, saying hey, you do not allow the charge to 3.6 volts and you do not allow the discharge to 2.5 volts. You are going to limit over here. So the BMS would act accordingly. So by doing this, you are not allowing the cell to be stressed at charge condition and discharge condition, which eventually would increase the life of the whole cell, whole pack, etc. So this is something which you have to do it, and yes, you have to slightly oversize the cell, so that even though by doing this kind of cutoffs there is some capacity lost, but still you are meeting the capacity which is needed for the battery pack. So this is something which you have to see. And also I would like to highlight a little bit over here, which is for the second graph. So if you see, there are different C rate graphs, 0.3C, 0.5C, 1C up to 3C. So if you see the green line which is for 3C, and if you are discharging the cell at 3C, you see that you end up quite before 105H. And if this is done quite often, you'll end up in loss of capacity. This is because the time required for the electrochemical reactions to happen inside the cell, you're not allowing that amounts of time. So which means the capacity or the reactions are incomplete, and if this gets continuous again and again, the half reactions are still half, and you're doubling that to happen, and that's how your capacity retention, the usable capacity, all falls down. Whereas if you see the purple line, which is 1C, that goes and ends exactly at 105 or even a little bit more, which means all the reactions, all the ion movements have all been transferred from cathode to anode and anode to cathode, and all the reactions are complete, which means you'll get higher life cycles, the required capacity, etc. So it is really important to see that the 3C discharge is limited for 30 seconds. If you're going more and more and more, you're going to lose your capacity.